Welcome back to Physics 192. I'm Gerard Blanchard. Last time we introduced alternating current circuits with inductors and resistors, otherwise known as LR circuits, L for inductor and R for resistor. Let's work a few examples. A 25 millihenry inductor with internal resistance of 25 ohms is connected to a 110 volt max source. If the maximum current in the circuit is 1.14 amperes, what is the frequency? And model the inductor as an ideal inductor in series with a resistor. So what you'll have to do here is you'll have to find the impedance of the inductor and resistor circuit, and from that you can find the inductive reactance, and from that you can find the frequency. So please try that. Let's draw our circuit. Here's our alternating current source, or alternating voltage source, I should say. Here's our resistor and our inductor. And this is a 110 volt max, so V max, or delta V max, is equal to 110 volts. And the frequency is unknown, that's what we're looking for. The resistance is 25 ohms, and the inductance is 25 millihenries, or 25 times 10 to the minus 3 henries. We are told that I max, the maximum amplitude of the current, is 1.41 amperes, 1.41 amperes. Okay, where can we go from there? As I said, the first step is going to be to find the impedance of the circuit. And we'll find that from I max is equal to delta V max over Z, the impedance. We can solve that for Z. Z is equal to delta V max over I max. So Z is equal to 110 volts divided by 1.41 amperes. So the impedance is 110 divided by 1.41. The impedance is 78.0 ohms. From that, we can find the inductive reactance. We know that the impedance is made up of the resistance and the inductive reactance, and that is Z is equal to the square root of R squared plus X sub L squared. We know that Z is 78.0, and that's equal to the square root of R squared, which is 25 squared, plus X sub L squared. So we're looking for X sub L. So 78 squared is equal to 25 squared plus X sub L squared, where what I've done is I've squared both sides of this equation. So I squared the 78 and got rid of our square root right there. Our 78 squared minus 25 squared is equal to X sub L squared. And I'll just go ahead and take the square root now. So that would be the square root of 78 squared minus 25 squared is equal to X sub L. And what is that number? The square root of 78 squared minus 25 squared is equal to 73 73.9 is equal to X sub L. So we found the inductive reactance. The inductive reactance depends on the inductance and the frequency. So X sub L is equal to 2 pi f L, or X sub L being 73.9. That is equal to 2 pi times the frequency times the inductance of 25 times 10 to the minus 3. And that gives us that 73.9 divided by 2 pi times 25 times 10 to the minus 3 is equal to F. And what is that equal to? 73.9 divided by 2 times pi times 25 times 10 to the minus 3, and that is equal to 470 basic metric units of frequency, which are hertz. So the frequency is 470 hertz. So given our inductance, that is the frequency that gives us the inductive reactance that we're looking for, and that gives us the inductive reactance that gives us the impedance, and that is the impedance that gives us the current that we observe. So the answer is a frequency of 470 hertz. Let's work another example. A 6.2 millihenry inductor is one of the elements in a simple LR series circuit. When this circuit is connected to a 1.6 kilohertz sinusoidal source with a peak voltage of 96.0 volts, a peak current of 2.5 amperes lags behind the voltage by 52 degrees. What is the impedance of this circuit? What is the resistance of this circuit? So from the maximum current and the maximum voltage that you're given, you can figure out the impedance of the circuit. And from the impedance of the circuit and the frequency and the inductance of the inductor, you can figure out the resistance of this circuit. Go ahead and try that, please. Here is our voltage source, our resistor, and our inductor. Delta V max of the voltage source is 960 volts. The frequency is 1.6 kilohertz, which is going to be 1,600 hertz. Kilo is 1,000, so 1.6 thousand is 1,600. The resistance, we are not given. We're looking for the resistance. R is unknown. L is equal to 6.2 millihenries, or 6.2 times 10 to the minus 3 henries. And we're told that I max is equal to 2.5 amperes. And we're also told that the phase between the current and the voltage is 52 degrees. Okay, that's everything we're told. We're looking for the impedance. and the resistance. Those are the two things that we're looking for. Well, we can find the impedance from the voltage and the current. I max is equal to delta V max over the impedance, or the impedance is delta V max over the current. So the impedance is 960 divided by the peak current, which is 2.5. So that gives us that the impedance is 960 divided by 2.5. It's 384 ohms. And then, just as we did before, we know that the impedance is equal to the square root of the resistance squared plus X sub L squared. Let's go ahead, actually let me square this first. Z squared is equal to R squared plus X sub L squared. So let's go ahead and calculate X sub L. X sub L is equal to 2 pi FL. X sub L is 2 pi times 1,600 for the frequency times 6.2 times 10 to the minus 3 for the inductance. So what does that give us for X sub L? 2 times pi times 1,600 times 6.2 times 10 to the minus 3. That gives us 62.3 ohms of inductive reactance. So X sub L is 62.3. So then down here we have Z squared. That would be 384 squared is equal to R squared minus 62.3 squared, or 384 squared, I'm sorry, that should be a plus right here, minus 62.3 squared is equal to R squared, or taking the square root of both sides, the square root of 384 squared minus 62.3 squared is equal to R. So what is the resistance of this circuit? The square root of 384 squared minus 62.3 squared is equal to 378 ohms is equal to the resistance, and that's what we were asked for. 378 ohms is the resistance of the resistor. Now let's add capacitors into our alternating current circuits. The alternating current in a capacitor is minus 90 degrees out of phase with the voltage, and the maximum is given by I max is equal to delta V max divided by X sub C, where X sub C is the capacitive reactance. So before, the inductive reactance X sub L is equal to 2 pi FL, the capacitive reactance is equal to 1 divided by 2 pi FC. Let's take a look at an example of that with our simulation. Here we have a circuit consisting of just a 5 volt, 500 hertz alternating voltage source and a capacitor, a 1 microfarad capacitor. Down here in the graph we can see the voltage. It is a sine wave. It starts from 0, goes up and down between plus 5 and minus 5. The current is 90 degrees out of phase with the voltage. Here is the peak of the voltage at this time, and at that point we see that we have 0 current through the capacitor. In fact, the peak of the current in the capacitor occurred when the voltage was 0. and it occurred before the peak in the voltage. So whereas the peak in the current through an inductor was shifted in this direction, in the positive direction, the peak of the current in the capacitor is shifted in the negative direction. So and it's also by 90 degrees. If this is 0 degrees, the peak of the voltage occurs at 90 degrees. This is 180, 270, and 360. So this is one complete oscillation of the voltage. So each one of these blue lines is 90 degrees. The peak of the voltage occurs here at 90 degrees. The peak of the current occurs here at 0 degrees. So the peak in the current is shifted by minus 90 degrees relative to the voltage. Let's take a look at the magnitude of the current. Let me write some numbers down. I have delta V max is equal to 5 volts. The frequency is 500 hertz. The capacitance is 1 microfarad, or 1 times 10 to the minus 6 farads. And the peak current is around, looks to be around 15 milliamperes. Actually, let's do our calculations and see if we get 15 milliamperes, give or take, maybe a little bit more than that. Well, X sub C is 1 divided by 2 pi FC. So X sub C would be equal to 1 divided by 2 pi times 500 times 1 times 10 to the minus 6. So that would give us a capacitive reactance of 1 divided by 2 times pi times the frequency, 500, times 1 times 10 to the minus 6. And that would give us a capacitive reactance of 318 ohms. Capacitive reactance is measured in ohms, just like resistance, inductive reactance, and impedance are, because they all appear in the current voltage equation in the same way. Namely, I max is equal to delta V max over X sub C, or I max is equal to 5 volts divided by 318 ohms, or I max is equal to 5 divided by 318, and that gives me 0.0157 amperes and 1,000 milliamperes is the same as 1 ampere. So that would be I max. Amperes cancel out. Is equal to 15.7 milliamperes. So just as we predicted from our simulation. Let's look at our simulation again. And here we see the peak of the current is occurring just above 15 milliamperes. So 15.7 sounds good. And so there you have it. That is the capacitive reactance. The capacitive reactance is 1 divided by 2 pi FC. The current in the capacitor is the voltage max divided by the capacitive reactance, and the peak of the current is shifted by minus 90 degrees relative to the peak in the voltage. So, bringing together alternating voltage sources with resistors, inductors, and capacitors, we have the alternating current in an LRC circuit, so inductor, resistor, capacitor, is 5 degrees out of phase with the voltage, and the magnitude of the current, the maximum current, is given by delta V max divided by Z, where Z is still the impedance, but now Z is equal to the square root of R squared minus the quantity X sub L minus X sub C squared. So what that means is that to get the reactance of the circuit, we take the inductive reactance and we subtract the capacitive reactance. And why do we do that? We do that because one is positive 90 degrees and the other is minus 90 degrees out of phase. So the inductive reactance, the capacitive reactance is subtracted from the inductive reactance to get the overall reactance. So this would be the same as saying that Z is equal to the square root of R squared plus the total reactance squared, where the total reactance is X sub L minus X sub C. So our impedance equation hasn't really changed in form. We've just added a new term, the capacitive reactance. And the same for phi. The phase angle is the inverse tangent of the reactance over the resistance, but now the reactance is X sub L minus X sub C divided by R. Let's take a look at our phasor diagram to see why this makes sense. Here is our phasor diagram where we have the current I max phasor along the x-axis. We also have the voltage across the resistor along the x-axis. We have I max times X sub L along the positive y-axis because the voltage through the inductor is positive 90 degrees out of phase with the current. And then we have to subtract off I max times X sub C because the current in the capacitor is minus 90 degrees out of phase with the voltage. So you see that what we have is on the side of our triangle, on the opposite side of our triangle, we go up by the current times the inductive reactance, and then we subtract off the current times the capacitive reactance. So the effect of the capacitor subtracts off from the effect of the inductor. And then our hypotenuse, the square of our hypotenuse, is I max times R squared plus I max times X sub L minus X sub C squared, which we can solve to get I max is equal to delta V max divided by the square root of R squared plus X sub L minus X sub C quantity squared. So you see that's where our new expression for the impedance comes from. The impedance is the denominator in that equation. And the phase angle is equal to the inverse tangent of X sub L minus X sub C divided by R. Let's work an example. A 300 ohm resistor and a 2.5 microfarad capacitor are connected in series across the terminals of a sinusoidal electromotive force with delta V max is equal to 120 volts with a frequency of 159 hertz. The inductance of the circuit is negligible, so L is equal to 0. What is the maximum current in the circuit? So what is I max in this RC circuit? Here's our alternating voltage source or our alternating EMF source, and we have a resistor and we have a capacitor. So delta V max is equal to 120 volts. The frequency is 159 hertz. the resistance is equal to 300 ohms, and the capacitance of the capacitor is equal to 2.5 microfarads, or 2.5 times 10 to the minus 6 farads. So we'll proceed as we proceeded throughout our alternating current circuits. We'll find the capacitive reactance. X sub C is 1 over 2 pi Fc, or X sub C is 1 over 2 pi times 159 times 2.5 times 10 to the minus 6, or the capacitive reactance is 1 divided by 2 times pi times 159 times 2.5 times 10 to the minus 6. That gives us a capacitive reactance of 400 ohms. Okay, now we proceed as we always have with the maximum current in the circuit equal to delta V max over the impedance, where the impedance is equal to, well, let me write delta V max again. The impedance is the square root of the resistance, R squared plus X sub L minus X sub C squared, and X sub L is 0. So I max is equal to delta V max 120 divided by the square root of R squared of 300 squared plus X sub L. X sub L is 0 minus X sub C, which is 400 squared, and all we have to do now is calculate. 120 divided by the square root of 300 squared plus 0 minus 400 quantity squared. And let's see, I have one parentheses too many. Okay, there we go. That would be 0.24. 0.24 amperes. And that is what we were asked to find. Let's work one more example. An RLC series circuit is connected to a 240 volt maximum power supply at a frequency of 250 kilohertz. The elements in the circuit have the following values. R is equal to 12 ohms. The capacitance is equal to 0.26 microfarads, and the inductance is 15.2 millihenries. What is the maximum current, and what is the phase angle? Please work that out. Here we have our alternating voltage source, and we have L, R, and C connected to that alternating voltage source in series, where delta V max is equal to 240 volts 240 volts. The frequency is 2.5 kilohertz, or 2,500 hertz. So 2.5 thousand hertz, or 2,500 hertz. L is 15.2 times 10 to the minus 3 henries, or 15.2 millihenries. That's L. The resistance is 12 ohms, and the capacitance is equal to 0.26 microfarads, or 0.26 times 10 to the minus 6 farads. Let's go ahead and calculate our inductive reactance and our capacitive reactance. X sub L is 2 pi FL, and so that would be equal to 2 pi times the frequency of 2,500 times the inductance of 15.2 times 10 to the minus 3. And what is that equal to? 2 times pi times 2,500 times 15.2 times 10 to the minus 3 gives us an inductive reactance of 239 ohms. And our capacitive reactance, X sub C, is 1 over 2 pi FC, which would be 1 over 2 pi times 2,500 times C, 0.26 times 10 to the minus 6. And what is that equal to? It's equal to 1 divided by the quantity, 2 times pi times 2,500 times 0.26 times 10 to the minus 6. That gives us 245 ohms. Okay, well, we were asked what is the maximum current and what is the phase angle. Our equations, as you should be familiar with by now, are I max is equal to delta V max over Z, and phi is equal to tan inverse of X sub L minus X sub C over not Z, over R. That's an R. I'll write it out. There we go. There we go. X sub L minus X sub C over R. And I max is equal to delta V max. Z, let's expand Z out. Z is R squared plus X sub L minus X sub C quantity squared. So we can go ahead and put in our values. I max is equal to delta V max of 240 divided by the square root of 12 squared plus 239 minus 245 squared, and phi is equal to tan inverse of 239 minus 245 over R, this is R, of 12. And let's go ahead and calculate these. I max is 240 divided by the square root of 12 squared plus 239 minus 245 quantity squared, And that gives us a current of 17.9 amperes. And phi is equal to the inverse tangent of the quantity 239 minus 245 divided by 12, and that gives us an angle of minus 26.6. So we have a negative phase angle because we have a greater capacitive reactance than we do an inductive reactance. So this circuit behaves more like a resistor capacitor than a resistor inductor. So there's more capacitive reactance to give us a negative phase shift than there is inductive reactance to give us a positive phase shift. So our answers are Imax is 17.9 amperes and our phase angle is negative 26.6 degrees. Let's talk about power in alternating current circuits. If you recall, the power through an electrical component in a direct current circuit is equal to delta V times I, or the voltage across that component, times the current through that component. We have a similar but different expression for power with alternating current circuits. The power in an alternating current circuit is given by P for power is equal to 1/2 delta V max, I max, times the cosine of phi. So the power in an alternating current circuit does depend on delta V max times I max, but we have a factor of 1/2 there. And the reason for that is that the voltage and the current are only at their maximum values for a very infinitesimally short time. Most of the time, the voltage and the current in the circuit have lesser values than their maximum values. So that's where the 1/2 comes in. It kind of gives us the average. So power is 1/2 delta V max times I max. Now we have a term, cosine phi. We have a term that depends on the cosine of the phase angle. And what that says is that the power is greatest when the voltage and the current are in phase, when they're oscillating together, or when phi is equal to 0. So the maximum of cosine phi occurs when phi is equal to 0. So when the voltage and the current are oscillating together, then we get the most power out of our alternating current circuits. When they are out of phase, we have less power, whether it's a positive phi or a negative phi. And if we go all the way to being 90 degrees out of phase, cosine of phi is 0. So the power can be anywhere from 1/2 delta V max I max to 0, depending on the cosine of phi. What that means is that a resistor for which the voltage and the current are in phase dissipate energy over time, whereas inductors and capacitors for which the voltage and the current are 90 degrees out of phase do not dissipate energy. They only store energy temporarily. Let's change this equation slightly by replacing Vmax and Imax with Vrms and Irms, where delta V RMS is 1 divided by the square root of 2 times delta V max, and I RMS is equal to 1 divided by the square root of 2 I max. When we use delta V RMS and I RMS, then our expression for power becomes delta V RMS times I RMS times cosine of phi. So if we use our RMS voltage and our RMS current, then we don't have the factor of 1/2 appearing explicitly. So using RMS voltage and RMS current, we have the expression power is equal to delta V RMS times I RMS times cosine phi. So you can see that if you substitute in 1 over root 2 delta V max for delta V RMS and 1 over root 2 I max for I RMS, that these two equations are the same. You get the factor of 1/2 delta V max, I max out of that. So what is this delta V RMS and I RMS? RMS stands for root mean square, and what it is it's the effective voltage or current. And if max or peak is not specified when you're told what the alternating current or the alternating voltage is, then you can assume that RMS is meant. So when electricians and electrical engineers talk about alternating voltage, they mean the RMS voltage, not the peak. But the RMS voltage and the peak or the maximum voltage are related by the expression delta V RMS is 1 over root 2 delta V max, and the RMS current and the maximum current are related by I RMS is equal to 1 over root 2 I max. And why do they use that? They use RMS because it eliminates that factor of 1/2 from the power. Power becomes the more familiar power equals delta V RMS times I RMS times cosine of phi. So if you're not told whether your voltage is the maximum or the RMS value, or if you're not told whether your alternating current is the RMS or the max value, you should assume RMS. We'll do some examples of power in alternating current circuits next time. Until then, think physics.